Okay, like it's not like yeah. If you're just like if it's not bleeding, or if it's not bleeding, it's like close.
It's a good thing.
It doesn't matter.
Oh, I'm so stupid.
It's not the best. It's just not the best idea.
Yeah,
Are we ready? So what I want to do today is just do a few more, just talk a little bit more about double integrals and volume. So pretty short. So let's say we have a problem, and we have this. We're setting up this double integral of. We want to find the volume. We want to find the volume under sine of y squared, and we're bounding this. R is our region. Bounded by 2y equals x, and x equals 0, and y equals 2. And we're going to set up our, so I'm not going to go through the setup, but we do go through the setup, and we find that we can evaluate this. Our answer is that we're going to do this double integral from 0 to 4, from x over 2 to 2 of sine of y squared, sine y squared dy dx. And that is the same. We set it up for both orders of integration, 0 to 2, 0 to 2y, sine y squared dx dy. And my question is which one do we evaluate and why? Yes, great.
Would evaluate it for why.
You want to evaluate this one first?
Yeah. No, the other one.
I think the one on the right would be easier.
You think the one on the right would be easier?
Yeah.
Do we agree?
Yeah.
Yeah?
No, I guess
No x's. Well, you made a good choice because the one on the left, that inner integral with respect to y sine y squared dy is actually impossible to integrate in closed form. So meaning you can't integrate it in terms of functions that we know, so you have to use a numerical method or something. So that first integral is actually not just difficult, it's impossible.
well, it's lucky that we chose the right one.
Lucky that you chose the right one, or you could be working for a long time. So let's evaluate this integral. So when we evaluate this inner integral, what do we end up with? So we get that our outer integral 0 to 2.
2 what?
What do we get for our
2 what?
2y times? Well, so this is y is constant with respect to x. We're integrating with respect to x. So we end up, the integral of is x sine y squared evaluated from 0 to 2y. So we end up with 2y sine y squared dy. And look at this. That's a gift, right? This is one of the easiest integrals that we've ever evaluated. Right?
Yeah.
This is just a straight u substitution. So what does this evaluate to? Sine y squared?
Straight up U.
Is it sine y squared? Minus cosine y squared? Evaluated from 0 to 2. And that evaluates to, if I evaluate that, I end up with 1 minus cosine of 4. So we change it from an impossible integral to, what's that? So let's see. I don't think so. Because we have the negative out front here. All right, you guys are thinking about the pi. Okay, so one really bad pi joke. Let's see. So we end up with this is minus cosine 4 minus cosine 0. Right? So this is cosine 0 is 1, but we have the negative sign, so we have a 1 minus cosine 4. All right. Are we all good now? So one really bad pi joke pun. Do you realize that 3.14% of sailors are pirates?
Hey, I posted out
Oh, yeah.
on Facebook yesterday.
Can't wait to get that up.
All right. Are we good? Are we good with this example? Okay. Next problem. Let's stay focused for just a little bit longer. R is a region in the XY plane. I'm not sure you guys need any sugar this early in the morning. Whose area is B. Without integrating, what is the... Oh, and let's see. I need to add one other thing before I ask the question. And f of xy equals k for all xy in R. So without integrating, what is the value of the double integral over R of f of xy dA and y? And k is a constant. What do you think, Anna? BK. So Anna says this is equal to B times K. And what? How did you come up with that? Okay. So our region here is just basically a right solid. So we have a solid with a base area of B in the plane, and our height of that solid is going to be K. So area of the base times the height. So this would be BK. And f of xy, if we think of this geometrically, what is f of xy equals k geometrically? A plane. And tell me a little more about this plane. It's flat. Flat meaning parallel to the xy plane, and the distance above the xy plane and Anna said was k. So it's k units. It's a plane parallel to the xy plane, k units above the xy plane, or k units away from the xy plane. Use geometry, right? All right. Last problem. Last problem. But no. For the power. So we want to evaluate this double integral. So let's so first off, let's looking at this, thinking about evaluating this double integral. Our first integral, the integral of 1 over the natural log y dy. Is that going to be an easy integral or a difficult integral? What do we think? We don't have a du for this natural log y to do a u substitution. So this one looks difficult. So what do we need to do? We need to switch our order. So this is difficult. So let's sketch our region. So our region, this says that e to the x is less than or equal to y less than or equal to 10, and we also have 0 less than or equal to x less than or equal to the natural log of, I switched these around. E to the x, oh that's right, natural log of 10. That's right. So let's sketch this region. So here's my xy plane. Here's e to the x. Here is y equals 10. I'll make that solid. And this is e to the y equals e to the x. And this is going to be x equals natural log 10. All right, so where is our region here? Our region of integration. Is it here, down here, or up here? Up, okay, so this is our region. All right, so let's switch our order. So we need to write our function in terms of x. So y equals e to the x. So x equals natural log y. Everybody good there? So when we switch our order, we're going to integrate from y equals 1 to 10. The integral, our inner integral is going to be x equals 0 to natural log y. 1 over natural log y dx dy. Look how beautiful this is. What happens when I evaluate this integral with respect to x? I just get x over the natural log of y, evaluated from 0 natural log y. And I just end up with 1. So this equals the integral from 1 to 10 of dy equals 9. Isn't that nice? So we twice today we turned things that were seemed impossible into something that was very easy.
Double integral should be like a motivational coach. You can do it.
And e to the x has just one more awesome property.
Yeah, go e to the x.
E to the x has one more awesome property.
Yeah.
Which one is that? It makes this work?
It has an area like a rectangle.
Right. Isn't that cool? Because the base here is
The area is just x minus 1.
right. Isn't that interesting? All right. That's one of the properties of the natural log function, is if you have equal intervals, it doesn't matter where you integrate, you get the same area. All right. Questions? Okay. Homework.